Well, guess what this is? This is the last screencast of 2020. After this, we are 5/9 of the way through apes. So the last thing for this unit is noise pollution. It's something that a lot of people maybe kind of think like, well, okay, so sound is an annoyance, whatever. But it turns out noise pollution is a real thing, and it is definitely something we should address. Okay, but before we can do that, we got to understand what sound is. So I don't know how much physics you've had. So I'm spent most of my time teaching physics, so I like to talk about the physics of sound. I find it pretty fascinating. So the idea is this: anytime an object vibrates, that could be like your vocal cords, it could be a trumpet, a guitar string, anything. When a physical object is vibrating, it tends to dissipate its vibrational energy by transferring it to the air particles or water particles around it. And then these particles will carry that energy away in the form of sound waves that move out in all directions at the speed of sound in whatever material they happen to be passing through. So the vocal cords of the dog are vibrating, and they're causing the air in its throat to vibrate, which causes the air outside to vibrate. And these vibrational waves are carried away. They carry energy away from the dog's throat, vocal cords in his throat, at the speed of sound in all directions by causing an oscillation of the molecules in the medium through which they're traveling, which in the case of this diagram here is air. So basically, it's worth knowing that sound is not something that is just something that travels through air. It travels through any material. So it's known as what's called a mechanical wave. So it can travel through gases, liquids, or solids. So, like for instance, if you've been underwater, you can hear a boat underwater. So clearly, it's sound. The sound travels through water. An earthquake, the P waves of an earthquake, the first ones that arrive, are just sound waves. And I really like this diagram here. So the thing to understand about sound waves is this: they manifest themselves as changes in pressure. So imagine if we have absolute quiet air, the molecules would be completely equidistant from each other, and the pressure would be very uniform, 1 atmosphere of pressure, let's say. Now, when things oscillate, so here I have an oscillating guitar string that's doing it in slow motion. Notice when it moves this way, it crams the molecules closer together. When it does, that causes high pressure. Then when it moves away, like here, it creates a zone of low pressure. And so these zones of high and low pressure travel away from this vibrating object. In this case, let's just say it's a guitar string at the speed of sound. So I'm just going to follow one of these compressional zones here. Look at this. I'm just following this zone as it goes this way, right? Here it is. It's still moving. It's still moving. All right. So all right, now our coming to this red dot. Now watch what this red dot does. This red dot is simply doing this. It's not going anywhere. It's just going back and forth. Sound doesn't move material in any place. It just causes it to go back and forth in place. What's traveling this way is sound energy. The material or medium, as we call it, through which is moving, is simply oscillating in place. Okay, so this could be air, it could be water, any liquid, any solid. So the regions where the molecules are clumped together, we call these things compressions. And compressions are regions where the pressure is higher than ambient or background, like silent. Okay. So if the air was perfectly quiet, the molecules would be the same distance apart. They call it 1 atmosphere of pressure. Well, in a compression, the pressure is going to be above 1 atmosphere of pressure. But in order to put a lot of molecules here, I had to take them from somewhere. So as the neighboring area has fewer molecules than it would in an ambient environment. So here in what we call a rarefaction, I like that word. In the rarefaction, the pressure is lower than 1 atmosphere. So no sound, 1 atmosphere. Compression, more molecules close together, higher pressure, more than 1 atmosphere. Rarefaction, less than 1 atmosphere. And remember, these compressions and rarefactions travel this way at the speed of sound, but the molecules themselves are simply going back and forth. Now, when we talk about sound, what we perceive is two different things. We perceive pitch and we perceive loudness, and they're different things. Okay, so pitch is basically like a very low pitch, very high pitch. Okay, it has to do with how frequently things are wiggling. So if things are wiggling slowly, then these compressions and rarefactions are farther apart. All right, and so they have what we call a longer wavelength, and this is oscillating with a smaller frequency. It doesn't wiggle as frequently, and so what we hear is a lower pitch. This one is wiggling with a higher frequency. You know, it's going back and forth more frequently, so it's a higher frequency. So therefore, it's making these waves more often. So the distance between these compressions is smaller. So we say it has a shorter wavelength, a higher frequency, and what we would hear is a higher pitch. So high and low pitches just has to do with is the air moving back and forth fewer times a second at a lower frequency. Then I hear a low pitch. If it's doing very fast, I hear a high pitch. Now, frequency is something that we measure in a unit called hertz. A hertz just means oscillations per second. So if that guitar string wiggles 20 times a second, it's going to make 20 compressions a second or 20 sound waves a second. So we say it has a frequency of 20 hertz. Now, when we were born, unless we had something wrong with us, most of us are born with an auditory range between 20 hertz and 20,000 hertz. What that means is if a vibration is happening in the air and it's wiggling less than 20 hertz, like 15 times a second, we don't hear it. If it's wiggling 25 times a second, we hear a very low tone. If it's going 10,000 times a second, we hear that 15,000 times a second. We hear that 18,000 times a second. We hear that 21,000 times a second. We don't hear that. So dogs can hear higher frequency. They can have up to 30,000 hertz. So a dog whistle is a whistle that makes a frequency of vibration that is higher than 20,000 hertz. So the humans don't hear it, but the dogs do. Similarly, elephants have been discovered to communicate subsonically, meaning that they use frequencies that are lower than 20 hertz, like maybe say 8 hertz. They hear it, we don't. So that's pitch. Now, the difference between loud and quiet and loud sounds, what we call loudness or volume, that has to do with the degree to which these compressions compress. So in other words, the greater the pressure in the compression and the lower the pressure in the rarefaction, that's what the difference between high and low pressure. So basically, when I cram these molecules together in a compression, the pressure goes up. Here's ambient. This is what it would be if there was no sound. In a rarefaction, the pressure is lower than what it would be if there was no sound. Okay. Now, if I make the same number of waves per second, we'll have the same pitch. But if I move the guitar, so the guitar string, let's say it's moving 20 times a second, it's going to make the same, well, let's say 200 times a second, it's going to make the same pitch, right? But if it's doing it with a small vibration, it's going to make small compressions that are not very high pressure. I'm going to hear that as quiet. If it's going back and forth a long distance, remember, it's still doing it 200 times a second, but it's going a greater distance, then it's going to make these compressions more compressed. The pressure is going to be higher, and I'm going to hear that as louder. So loudness has to do with the amount of pressure produced in these, whereas pitch has to do with how frequently they're produced. Now, loudness is something we measure with something you've probably heard of called a decibel. So a decibel, and it's a little bit of a tricky, and we don't have to get really into it, but it has to do with our perception as well as the actual pressures. So we measure sound levels in decibels. So basically, exposure to things over 70 decibels can begin to damage our ears. So prolonged exposure to 70, 80, 90, 100 decibels, that can cause hearing loss. Exposure to sound levels over 120 can cause your ears to ring, and that means basically you're experiencing immediate hearing loss. If your ears are ringing, you've damaged your ears permanently. That's one thing you got to understand about hearing. It's permanent. You damage your ears, you cannot fix it. So you got to be careful with them. And here's a graphic I think is probably interesting. Okay, so normal breathing is not very loud, 10. This mosquitoes that get in your ears, man, 20 decibels. All right, we keep going. So normal conversation, 50 to 65 decibels. All right, and then we start getting to like a vacuum cleaner, 70. So like if you spend your day around people in normal conversation, your hearing is never going to be damaged by it. But now you're spending your day around some kind of equipment that's making these noises, and these aren't particularly hugely loud noises, but they're loud enough. If you have prolonged exposure, you're going to end up with some hearing loss. Now, when I get to like 85, 90, 100 decibels, that's when I start doing damage to my ears pretty quickly. So when sound levels get up in this way, like from, say, basically, especially from like 100 and on up, then it tends to cause some pretty rapid hearing loss. So let's see how this happens. Okay, so here's a diagram of your ear. If you couldn't tell, here we see sound waves coming in. So when When a compression is on this side of your eardrum, which is also called your tympanic membrane, when a compression here has got high pressure, so it pushes your eardrum in. When there's a rarefaction, the pressure outside is low, so the air behind your eardrum will push it outwards. So basically, if sound waves are coming in 200 times a second, then they're going to push your eardrum in and out 200 times a second. So it's going to wiggle the same frequency as, say, the guitar string that's making these sound waves. And they flex these little bones here, these three little bones, okay, the hammer anvil bones, and they set up motion in the liquids of this thing here. So this is called your cochlea or your inner ear. And this is where you're going to turn mechanical waves into electrical signals of nerve cells that carry it to your brain, which you can then interpret as sound. So this little magical device we have here called a cochlea is a really valuable organ in your body that you may not even know you have. Now, this part here we'll ignore. This has to do with our ability, weirdly, to perceive up from down. If you have a damage to this, you tend to get dizzy. It's pretty awful. My sister-in-law has that. So here's your tympanic membrane, your eardrum. Here are the little bones attached to it. This little one here, I think it's called a stap, moves back and forth and it sets up oscillations in the liquids in this coiled snail-looking thing called your cochlea. And this is basically, here's your auditory nerve. So this is nerve signals from here go to your brain, and that's how you interpret sound. So what you find inside the cochlea are a bunch of these little hair cells. At the base of each of these little hair cells, there is a nerve. So if this hair wiggles, then it triggers a nerve impulse which goes up to your brain. The bigger the wiggle, the more aggressively it wiggles, the stronger the electrical signal that it sends to your brain, which you interpret as loudness. Certain hairs are tuned to certain frequencies. So short ones tend to wiggle for high frequency waves, and longer ones tend to wiggle for lower frequency ranges. And so, basically, as sound comes into your ear, if all the hairs are in place, then you have hairs that can wiggle 20,000 times a second and ones that can wiggle 20 times a second, and you can hear that full range of sound. But what happens is this. So over time, these hairs wear out and break, just like a car breaks down over time through excessive use. Same thing happens to these hairs. So this is an electron micrograph showing the arrangement. They tend to occur in these chevron patterns, which is kind of interesting. So you have these chevron patterns of these hairs. Remember, you got these short ones, longer ones, and collectively they can hear all these different frequencies. But what happens is over time, exposure to loud sounds, especially, causes this large flexing of these, and then they break. And when they break, they're gone, and they don't grow back. And you can tell this happening if you hear a really loud sound afterwards. You're like, "Bee!" Basically, that's hairs that have lost the hairs that have broken, and the nerves don't know what to do, and so they're just sending a signal to your brain like, "I don't know what I'm supposed to do," and you can actually end up with a condition called tinnitus. I have a friend, teacher here, I'm not going to name names, who always hears this buzzing sound. It's awful. It's like you can't make it go away. These nerve cells are like, I've got to send a signal to the brain, but my hair is gone, so I don't know what to do. So just be. So tinnitus is a particularly unfortunate consequence of hearing loss. You don't want to lose your hearing. You need to protect it, and there's things you can do. So basically, when you're born, you've got all those hairs. You can hear from 20,000 hertz to 20 hertz to 20,000 hertz. But then what happens is, as you get older, especially the louder you listen to, so like if you put headphones in your ears and you listen to music really loud, or you just go to concerts where you hear really loud sounds, or you work in a place that has loud sounds, like jet engines, or my brother-in-law worked in a metal shop. When you have these loud, especially high frequency sounds, you wear out those hair cells pretty easily. And so what I want you to do at home is this. There is a tone generator I want you to take. So now it's pretty scary. So I'm going to click on this here, and I'm going to play this. Okay, that's 440 hertz. The conversation can be like, okay. Now, I imagine you hear that. I hear that. Okay, I'm going to make it go up. 800 hertz. I definitely hear that. 1300 hertz. Yeah, I hear that. But watch, it's going to be pretty wild. I can hear 2000 hertz just fine. 3000, I'm good. 5000, yeah, I hear that. Oh yeah, I can hear 650. 8000, you bet. Guys, I don't hear anything. You probably hear something. I don't hear anything. I'm not even to 9,000. I've lost half of my range of hearing already. I'm 58 years old. Half of my hairs are gone. I can't hear that. It's going to happen to you too. It's going to happen to you sooner than it did to me because I didn't grow up with headphones in my ears. Okay. So I'll try so it doesn't drive you crazy anymore. Okay. So the point I'm trying to make here is just this is that that you should protect your ears because once these hairs break, they're gone. Now noise pollution is something we're going to worry about it because it can do so how do you protect your ears? Well, try to avoid prolonged exposures to sounds that are between 70 and 100 decibels. Now I'm wondering, is it psychological? I think I hear something, but I don't know. Wait a second. Oh no, is that still going? No, it's not. Okay, it was all in my head. Okay, and definitely avoid like gunshots and lightning and explosions, fireworks, things like that. Jets, they're close up. Those are really loud sound. And so when you get exposed to things over 120 decibels, it's like instantaneous hearing loss. So now noise pollution, because this is a unit on pollution, noise pollution is basically anthropogenic sounds, like human made sounds, that are above 75 decibels. So, what are some of the sources? Well, obviously, traffic. Okay. If you ever walk along a road, man, it just drives you nuts. It's really, really loud. Jets, especially if they're flying low, construction sites, jackhammers and saws and hammers. If you live near a nightclub, or I've been traveling and rented a hotel and it turns out to be right next to a nightclub, you can't sleep at night. Okay, or the neighbor's dog, even dogs can bark at like 80, 90 decibels, depending on how far away you are. So these are all sources of. I won't call the neighbor's dog anthropogenic because the dog wouldn't be there if it wasn't a person who had it. Okay, and so these things produce what we call noise pollution. And you might think like, well, okay, so it's kind of annoying. No, actually, it's a real problem. Okay, so here's why it's a problem. Why do things even hear at all? The reason that hearing evolved was to help us detect predators. So it's protection from predators. I hear them coming, and that puts me into this fight or flight mode. And so, what is the fight or flight response? Well, our blood pressure goes up, our pulse begins to race. Uh, we're on high alert. We experience stress. Well, all of this is damaging to the body. If prolonged exposure to this causes hardening of the arteries, it causes stroke, it causes heart attack. And you might think like, oh, right. It actually, epidemiologists have done studies, and what they found, like there's a really important one in Europe recently, and they said, look, in Europe alone, that's where they limit their study to. They did the math and like, well, it seems like this, like people who live closer to these loud sounds have higher incidence of heart attack and stroke. And what they decided was that about about that's going to be an ad that about 50,000 Europeans a year die because of heart attacks and strokes caused by noise pollution. So it's not trivial. It's real. Also, it interferes with our ability to sleep. So if you have loud noises at night and that interferes with your ability to sleep, that can be really bad because a lack of sleep, as every Korean student knows, leads to stress, fatigue, memory loss, depression, and it can even lead to things like substance abuse, alcoholism, just because people self-medicate when they're feeling the effects of a lack of sleep. And noise pollution definitely can lead to a lack of sleep, especially in urban areas. Now, in addition to harming humans, noise pollution also affects animal species because animals, evolved hearing to basically alert themselves to the presence of predators, but they also use it to find prey items and to do other things. So they use it to like mark territory. That's why your dog barks. Uh, they use it to find mating partners. That's why birds sing. They use it to communicate for migration purposes, like whales when they're migrating call to each other, elephants call to each other this way, and certain things like bats and cetaceans, like dolphins and humpback whales, no sperm whales. Uh, they use echolocation. They make sound waves and they use it to find their prey. And noise pollution interferes with all of those things. And so let's just look at a couple of them. Okay, the place where I live in the States has a very large naval facility, a submarine facility in particular, and they use sonar to try to locate their opponents. So they are often testing these very, very loud sonar waves to try to uh, uh, improve their ability to detect enemy warships. Well, that's a real problem because like some of these sound waves they're making are like we're talking like 235 decibels. I mean, it's crazy loud. It's like deadly loud. And so what they're finding is it's causing a lot of stress in species that are important and endangered, namely like different whale species. Also, too, they're finding that some whale species are becoming stranded on beaches. Like they're not able to detect the presence of land when they need to because of this. It's also interfering and stressing out orca whales and dolphins who use echolocation as a way of locating mates. So it just turns out shipping traffic and especially sonar and sometimes sonar is used by as a way of trying to locate oil deposits. So all of this tends to put stress on these uh, aquatic organisms. Now, urban noise pollution caused by cars and nightclubs and construction stuff like that is definitely caused. It's been demonstrated in the scientific research shows that it's changed the behavior of bats. It's interfered with bats' ability to find insects. So what happens is the bats they get hungry, so they just stay out of the cities. Well, that's a problem because bats, a lot of bats are insectivores. People don't like insects. Insects cause diseases and stuff. Well, normally these bats do provide an ecosystem service of eating these insects that would otherwise be harmful to us. Well, guess what? The bats go elsewhere. They might roost near the city, but they don't hunt there because it's too hard for them to find their prey. Bird species have been seen to alter their migratory paths because when they stop, they communicate to each other by vocalizing, and they can't hear each other. So what they do is they avoid these loud areas. Well, when they do that, then you know they're normally part of that ecosystem, and now they've removed themselves from that ecosystem voluntarily to get away from the sounds. And a consequence of that then is that there's a decrease in richness in that ecosystem because certain species have opted to stay out because they can't hear each other. Um, there have been studies where she's saying that birds change their how loud they sing, what notes they sing, what time of day they sing. So there's definitely clearly changes in bird behavior in response to noise pollution. Another study that was kind of interesting found that prairie dogs who live near roads, when there's the more noise there is on the roads, the more they change their behavior. So when there's a lot of cars, they get this sort of alert, looking for trouble because they're stressed out, and they're not foraging for food. So that's definitely going to affect the prairie dog's ability to, over time. This leads to a lack of proper nutrition and increased stress levels have a negative health effect on the populations. So what can we do about this? Okay, education. Like if people know about it, they know it's more than just a nuisance. They might respond to it differently. So most people don't think of noise pollution as pollution, but it is, and it's definitely something that has negative consequences for both human health and animal health. So we need to educate people to that. One thing is the use of electric vehicles. The first time I went to Beijing, it was so freaking loud. It was amazing, right? And I went there maybe 3 years later. And the air was cleaner. I could see blue sky, which was wild. And it was almost unnerving how quiet it was because there just wasn't any. They basically switched almost entirely to electric vehicles. Now it's a little bit scary. You can get run over, but it definitely made it a lot quieter. And the other thing too is like in some cities like New York City and Delhi and places, people are honking constantly. It's like, why are you honking? Nobody's listening. You stop honking already. Sometimes they have rules. You're not allowed to honk. Okay. Now, one thing I noticed in Korea is there's a lot of sound barriers along the highways. I think it's a great idea. So if you live in an apartment near a highway, it can be awfully noisy. So they put in sound barriers to deflect the sound and keep it from going into people's houses. So that's good. Another thing you do is certain areas are designated quiet zones, especially in national parks. So make it so that there are regions that we set aside to keep the sound down, or we can separate airports from urban areas so that the sound of the jets don't affect people. Like when they build new runways and stuff, there are people who suddenly their houses are so loud that they can't sleep at night. Well, it's more than a nuisance. It's something that causes death. So we have to be quiet with that. Um, you have town ordinances that say, there's certain places that have to keep the sound down at certain times of day. And the other thing we do is we can restrict the use of sonar in oceans. Okay, there's my ride. I'm going to go, but thank you. It's been a great year. Although I got to tell you, I'm ready for 2020 to go away. Take care.